In this slide deck, we will introduce the Bernoulli Trial, which is the workhorse of introductory courses in undergraduate probability. The Bernoulli Trial is a single coin toss. When looking at the binomial distribution, the experiment of interest is, instead, a series of coin tosses. In both sections, we will state the physical system being modeled and look at the corresponding probability distribution, average, and variance. We manifest the Bernoulli Trial by tossing a penny once. We represent the possible outcomes using the single variable x. If we obtain no heads, meaning tails, we say that x equals 0. And if we obtain heads instead of tails, we say that x equals 1. X is the number of heads we obtain from an individual toss. Depending on the fairness of the coin, the outcome of tossing a coin 100 times might be, for example, 60 heads and 40 tails. We can express this probability distribution in terms of numerical frequencies. By convention, p represents the fraction of tosses that land with heads facing up, meaning the fraction that produces so-called success, and 1 minus p represents the fraction of tosses that produces tails, also called failure. The two frequencies 1 minus p and p must add up to 1. What is the average number of heads? Using the definition we learned in the previous video, we take a sum over values of x using the probability distribution p on x as a weighting factor. For a large number of trials, we get the result 0 heads, 1 minus p of the time, and we get the alternative result 1 heads, p of the time. Because there is a 0 in the first product, only the second product, namely 1 times p, survives, and so the expectation value of x equals p. What is the variance of the number of heads for individual tosses? Using the definition from the previous video, we take a weighted sum of the square of the deviation of x from its average value. When the outcome is x equals 0 heads, the squared deviation is the square of 0 minus p. This occurs 1 minus p of the time. When the outcome is x equals 1 heads, the squared deviation is the square of 1 minus p, and this outcome occurs p of the time. The square of 0 minus p is simply p squared. Both terms contain at least one factor of p and at least one factor of 1 minus p, which can be factored out front, leaving behind in the square brackets p plus 1 minus p. But this is just 1, so the variance in the number of heads x is simply p times 1 minus p. We have just studied the probability distribution and statistics for a single coin toss, as summarized to the left. As summarized to the right, we will now investigate the probability distribution and statistics describing the outcomes of a series of tosses. Consider tossing a coin n times. In this cartoon, we will illustrate tosses 1, 2, and 3 concretely. The outcomes, whether we obtain heads for these tosses, are individually x sub a, x sub b, and x sub c. When tossing a coin 3 times in a row, we can obtain a variety of outcomes. Each outcome is specified by determining whether the first toss lands heads or tails, whether the second toss lands heads or tails, and whether the third toss lands heads or tails. If the probability of landing heads on any individual coin toss is p equals 1/2, then the probabilities for these 8 illustrated outcomes correspond to slices of a pie chart divided into equal areas. However, if p takes a value differing from 1/2, then the pie becomes biased and the areas of the slices uneven. Some configurations become more likely than others. Our purpose is to write down the probability for obtaining a particular total number of heads, x equals x sub a plus x sub b plus x sub c plus so forth, from capital N tosses, given that each individual coin toss is a Bernoulli trial with probability p. What is the probability of a particular sequence? Assuming that individual coin tosses do not influence each other, we say that they are statistically independent. Thus, we say that the probability distribution for getting the sequence string x sub a, x sub b, x sub c, etc. factorizes into a product of individual probability distributions, p sub a on x sub a alone, times p sub b on x sub b alone, times p sub c on x sub c alone, and so forth. If, for example, we are interested in the sequence tails, heads, heads, which we also call 0, 1, 1, we write down the fraction of time that the first toss lands tails. Out of that portion of the pie chart, what is the fraction of time that the second toss lands heads? And out of this portion of the pie chart, what is the fraction of time that the third toss lands heads? The chance that the first toss lands tails is 1 minus p. The chance that the second toss lands heads is p, and the chance that the third toss lands heads is also p. More generally, the probability for getting the outcome sequence x sub a, x sub b, and so forth is a product of two terms. P is taken to the number of heads, that's x, and 1 minus p is taken to the number of tails. The number of tails is the total number of tosses, capital N, minus the number of outcomes that are heads, that's x. How many ways are there to obtain the same total number of heads? In addition to the particular sequence tails, heads we have so far considered, there are two additional ways in this pie chart to obtain 2 heads and 1 tails out of 3 tosses overall. We get different outcomes by rearranging the sequences of the outcomes of the individual tosses. There are 3 ways to get 2 heads and 1 tails. More generally, there are a combinatoric factor, n factorial over n minus x factorial many ways to get x heads out of n coin tosses, as the viewer can review using the video tutorial on enumerative combinatorics. The probability of getting 2 heads out of 3 coin tosses is a product of a combinatoric factor that specifies the number of slices of the pie chart that satisfy this condition, here that's 3 slices, multiplied against the size of a slice, which is the same for each of those 3 ways. The probability of getting x heads out of n coin tosses is a product of a combinatoric factor, that's n factorial over n minus x factorial, and a size factor, p to the x times 1 minus p, that 1 minus p quantity taken to the n minus x power. This probability distribution is called the binomial distribution. Now that we have described the pie chart to the left, we will present a couple examples of its associated statistics. What is the average total number of heads obtained from many experiments, each of which consists of n coin tosses? Well, we could directly substitute the probability distribution from above into this weighted sum. We instead recognize that x is a sum over individual outcomes, x sub a plus x sub b plus x sub c and so forth, so we will calculate the average of the sum, here that's x, by writing down the sum of the averages of the outcomes of the individual tosses. The tosses have the same probability distribution and associated statistics, so this sum adds up n copies of the same expectation value for the number of heads on an individual toss. In the previous section, we showed that this expectation value is p. The average total number of heads is the number of tosses times the probability p of success on any individual toss. What is the variance in the total number of heads? While again we could directly substitute the probability distribution into this weighted sum for the square of the deviation of x from its average value, we will instead remember that the individual coin tosses are statistically independent. This means that the variance of the sum equals the sum of the variances. The variance associated with the total number of heads equals the sum of the variances associated with the numbers of heads on individual tosses. Because the tosses are described by the same probability distribution and associated statistics, this corresponds to n copies of the same variance for the number of heads from an individual coin toss. In the last section, we derived that the variance for a Bernoulli trial is p times 1 minus p. In this slide deck, we have presented the Bernoulli trial and the related binomial distribution. Despite, or perhaps by virtue of, their simplicity, the basic processes, probability distributions, and statistics summarized on this slide serve as workhorses for introductory courses in probability. These distributions are often used as the starting points from which special case distributions are derived.